Hello, Honors Algebra 2. A quick video here covering a topic that we're going to have a few homework problems on, and you're going to see this in the future, next year, and beyond in calculus. We are not going to have a question on this on the MCA this week, but we may have a question on it on the test for this chapter later. Okay, so in geometry, you likely remember learning a formula for arc length when we are measuring angles in degrees. And the formula looks like this. Arc length. Oh, by the way, often S is used for arc length. So arc length is shown over here. It's the red arc. And arc length is equal to theta over 360 times the circumference. And if the radius is r, the circumference, of course, is 2 pi r. Now, why does this just make sense intuitively? Theta over 360 is a ratio of the circle. So theta is this angle. In degrees, 360 is this angle. So what fraction of the circle is represented here? On what fraction of the circumference is the red arc? Well, the fraction is whatever the angle theta is divided by 360. And we multiply that fraction by the entire circumference, and we get the arc length. Okay, so this is the formula in degrees. And what you're going to see here is one way that the radian system appears to be a more like natural system of measuring angles, because radian measurement is based on pi. It's based on the number pi, which is the fundamental ratio of a circle. So let's do the exact same formula in radians. So in radians, I'll do it in green. So in radians, we have the following. We have arc length is equal to a fraction of the circumference. I'll put fraction times circ. So what would that be? The arc length is theta over, now instead of 360, since we're in radians, it's theta out of 2 pi. A complete circle is 2 pi. Well, the circumference is 2 pi r, and you can see that when we have the formula in radians, the 2 pi cancels, and the arc length formula is theta times r. Okay, so because radians are based on multiples of pi and fractions of pi, which is also the ratio we use, or the way we calculate circumference, these values cancel. We get a very natural formula for arc length. Okay, so here, if you are ever trying to find arc length when you're working with the radian system, the equation for arc length is theta r. Okay, what about sector area? So let me erase this quickly. And so now sector area would be the area of, let's see, I'll do it in, how about I'll do it in blue. Sector area is the area of this pizza slice. And a sector of a circle is this wedge shape. And in degrees, the area would be theta out of 360 times pi r squared. So it is a fraction of the whole area. This is also in degrees. In radians, sector area is theta out of 2 pi. There's your fraction of the circle, that's the fraction that I've shaded, times pi r squared. So we get a nicer formula, which is theta r squared over 2. All right. By the way, this is what the formula you see in green here shows why we often think of angles as being dimensionless. We measure angles with a unit, and our unit of measurement is either degrees or radians, but that unit does not provide dimension. And if we think about it here, look at this formula. Arc length is theta r. Let's say the radius was measured in centimeters. Then the arc length would be measured in centimeters. So theta can't be providing a unit that creates a dimension in the calculation. So r is in centimeters, arc length is in centimeters, so theta is just a ratio. You may remember that theta was actually defined to be the arc length divided by the radius. So arc length is just a ratio, like a percentage, similar to a percentage. Okay, so area. What are the units of r squared? Let's say radius is in centimeters. So the units of r squared would be centimeters squared. Well, that's the same as the area, so theta can't be providing a dimension in the calculation. Okay, so the arc length, an arc length is a portion of the circumference of a circle. The equation for arc length S with radius r and central angle theta measured in radians is S equals r theta. Got to memorize that. And the area of a sector is A equals theta r squared over 2. Okay, a couple just quick basic problems. So we have a problem here. Find the perimeter and area of a 60-degree pizza slice of a large pizza whose diameter is 14 inches. Okay, so we have a pizza, and we've got a slice that's 60 degrees. Let's see, that's about 60 degrees. And the diameter is 14 inches. And since the diameter is 14 inches, that means the radius is 7. Now, 60 degrees as an angle is the same as pi over 3 in radians. Now, I wrote the word radians because I'm doing a conversion. As we stated in class, you actually don't need to write radians. Whenever you write an angle with no unit marking at all, the assumption is the angle is in radians. Let's use our radians to actually answer this question. So we want to know, it says find the perimeter and area of this slice. So what would the perimeter be? Well, the perimeter would be this side, 7, this side, 7, and then the arc length, S. So the perimeter would be 14 plus the arc length, which is, let's see, that would be theta r. So theta r, perimeter would be 14 plus pi over 3 times 7. So the perimeter is 14 plus 7 pi over 3. I'll just leave it like that. And it says inches, so this is inches. There we go. And the area of this pizza slice would be 1/2 theta r squared. That's our formula in radians. I'm going to use the radians formula. So the area is 1/2 pi over 3 times 7 squared. And what do we get? 49 pi over 6 inches squared, since we are in inches. Okay, simple, quick problem with that. I don't know why I have two problems numbered number 1 at this back to back, but An arc of length 120 inches is measured on a circle with radius 24 inches. So let's draw that before I even go on. A circle with radius 24 and an arc length of 120 inches is measured on a circle with radius 24 inches. How big is the central angle that cuts off this arc? How big is the area subtended by this arc? Okay, we'll talk about that in just a minute. So we have S equals theta r, that's our arc length. And they gave us that the arc length is 120 and the circle has a radius of 24 inches. So it's pretty simple. We just plug into this formula, theta 24, and divide that, and we get theta equals 5. So we check our units. Well, this is in radians because we use the radians formula. So I write nothing, and the assumption is if I have an angle with a number and no unit marking of any sort, then that's it. It's 5 radians. By the way, 5 radians. So remember 1 radian is just a little less than a third of a circle, is about 57 degrees. So that means, and remember that a half turn is pi, that's a little more than 3. So a full turn is 2 pi, that's a little more than 6. So 5 radians would be somewhere over here, kind of like in that direction. It's not perfect. I'm not quite right, but because you can't get it exact. 5 radians is hard to draw exactly. So the arc length of 120 inches is the corresponding arc length around the circle to that spot. Okay, and that is S equal to 120, and this inner arc is 5 radians. Okay. Yeah. So, I also want to find how big is the area subtended by this arc. That is the language you may have seen in geometry for finding the area of the sector created by this central angle. So then that would be what? A equals 1/2. So again, you need to really memorize these two formulas. They come up in a lot of applications, not a lot, but they come up in applications that you'll see in the future in pre-calc and calculus. Okay, so we got our formula, area equals 1/2 theta r squared. 1/2 theta r squared. And we want to know the area. It's 1/2 times 5 radians times 24. So the area is, let's see, 24 divided by 2 is 12. So what would I get? 5 times 12. So the area is 60 inches squared. All right, that's it. Quick video, and you'll have a couple homework problems on this. I'll see you in class.